Let's add a couple of more details about CO2 through the Earth history. This one is probably something you have seen before. This is from the Vostok ice core in Antarctica, which shows ice core data from the Dome Sea, I think, or whatever it is from Antarctica. I should know, but anyways, you can see these ice age cycles at about 100,000 years that have occurred in the last million years or so, which is the Pleistocene. And here we are in the modern age, what we call now Anthropocene. So there we were in 1950, and then we are headed up and up at about 4 ppm per year. As we said, doubling this number gives us the amount of CO2 in the atmospheric reservoir, but ppm is easier to track, and it's a well-mixed gas, so you can measure it anywhere in the hemisphere and you get a good sense of the global average. Of course, associated with this, there are changes in temperature, which there are details in terms of how fast methane and CO2 are rising versus how fast the temperature is rising, because in these cases it was the atmospheric radiation change because of the orbital parameters like obliquity, ellipticity and precession that were creating perturbations. So you can see there is a rapid warming phase and a slow cooling phase. So buildup of glaciers takes time because of feedbacks between the reflectivity, ice buildup, atmospheric temperature, humidity, snowfall rates and so on and so forth. But the warming phase or the melting of the glaciers goes really fast. Unfortunately, we are in the melting phase, which means we are looking at potential runaway melting of glaciers on Antarctica and Greenland, and you hear lots of stories about glaciers curling off and floating away and so on and so forth. And we also hear about how much sea level is locked up in those things. So we'll come to some of those details in the context of the carbon cycle. Ocean carbon cycle has some really interesting behaviors. CO2 dissolves easily into the water, but the ocean doesn't get saturated very easily because the H2O plus CO2, which produces carbonic acid, is moved around into bicarbonate and carbonate ions, and then there is the calcium carbonate, which is used up by corals and other shell-forming animals. So there is what is called a buffering, which we will look at later, because the dissolved CO2 can be moved into different compartments, so it's not easy to saturate. But if you move this increased CO2 too rapidly, then these reactions don't go as fast as they can in an equilibrium situation, in which case you begin to affect the consumption of the carbonate ion, so that begins to cause what is called ocean acidification or dissolving of the carbonate shells, because calcium carbonate will not be saturated in the surface waters anymore. I'm going a little fast, but we'll come back to these details later on. So the measurement of that is in terms of the pH, which is of course something you learned in high school in terms of the log of the negative H ion concentration. Ocean has remained at about 8.1, 8.2 for many million years because of this buffering ability. But as you increase CO2, you push the system away from the bicarbonate flattening area here, and you begin to reduce carbonate, and you begin to reduce pH, which is what we call sorry, acidification, and that's not a good thing, right? So we'll come back to that. Or the geologic past, you can see here, looking at the 800,000 year time scale again, atmospheric CO2 has varied by about 100 ppm between glacial and interglacial or ice age and non-ice age periods, and glacial interglacial pH has basically varied between this value of 8.15 to 8.25 or so. But the projections are that if we keep emitting CO2 at the rates that we are, then pH could drop pretty precipitously, and already some of the corals are severely damaged and so on. Over the life of the Earth's history, formations of 4.5 billion years ago with the solar system, Sun was actually 30% less luminous when we started. So then the question is, what was the temperature if there was no atmosphere versus if there was an atmosphere present? And the key question there is, with 30% lower energy coming from the Sun, how did Earth keep water in its liquid phase, which there is evidence for? So there are many hypotheses, and the idea is basically that to stay above freezing, we probably had methane as the main greenhouse gas. CO2 was not dominant, and O2 was definitely not in its current levels in the free atmosphere, which is at 20%. So all those details are there in many books. That's called faint young sun paradox, first named so by Carl Sagan, the famous astrophysicist, cosmologist. And the CO2 story here is that as Earth got more luminous and energy input increased, what happens is when there is less energy and temperatures are colder, the weathering rates are slower, so atmosphere builds up CO2 because weathering would take down CO2 and dissolve calcium carbonate from the rocks and so on. And as Sun got more luminous and temperatures went up, weathering rates would go up on these geologic timescales, and that would draw down the carbon. So carbon again is a key player on these slow geologic timescales. As I said, carbon dioxide is often talked about in terms of gigatons, which is a billion metric ton, or 10 to the 15 or petagrams of carbon or carbon dioxide. So carbon and carbon dioxide are related by these issues. I think you are all aware of what a mole of a substance is. So if you think about CO2, it's not 1 gram of carbon mixing with 1 gram of O2. It's 1 mole of carbon reacting with 1 mole of O2 and forming this oxidized form of carbon. Its oxidation state in this case will be +4 because oxygen takes away 4 electrons from carbon because it's electron hungry. So carbon is left with +4 charge. So that's the oxidation state. In methane, for example, it'll be reduced state with -4 because hydrogen gives electrons to carbon and so on. Nonetheless, carbon molecular weight is 12 grams, so 1 mole of carbon will be 12 grams. 1 mole of O2 is 32 grams, so you have 44 grams of carbon. Out of that, 12 grams carbon dioxide, out of which 12 grams is carbon. So if you want to go from 1 gram of carbon to CO2, you will need to multiply it by 3.7. So 3.7 gram of CO2 has 1 gram of carbon. Okay, very simple, but it's better to remember. The Young-Sun paradox and methane to CO2 evolution of the O2 producing phytoplankton and then the plants, vascular plants and so on, have controlled the evolution of oxygen through this Earth's history. So we used to be at less than 10%, close to 0% of the current levels, and then we have vacillated around and settled to the current levels of 20%. So we have various evidences by which we infer these things, but I won't go into the details. But right now we are burning CO2, so we are consuming O2, which is measured surprisingly by, well, I don't know, coincidentally by the son of the person who started measuring CO2, Charles Keeling, started measuring CO2 in the 50s on Mauna Loa. His son Ralph Keeling started measuring oxygen, I think, in the 1980s or 90s. Okay, So that's the story of carbon dioxide in Earth's history, and oxygen through Earth's history, and pH through Earth's history, and so on. Once we are oriented with this, we will start going into the details of the global carbon cycle, which is, as I said, basically a brief introduction, but it's very useful for people who want to do Earth system science, global warming, and so on. Many people come at it from atmospheric dynamics, ocean dynamics, climate dynamics, but carbon cycle is an indispensable part of it, so it's better to be exposed to it at this level of basics.